So for number 17, we've got a zero point 0.4 kilogram object connected to a light spring with a force constant of 19.6 newtons per meter, oscillates on a frictionless horizontal surface. If the spring is compressed 4 centimeters and released from rest, determine the maximum speed of the object. B, the speed of the object when the spring is compressed 1.5 centimeters. C, the speed of the object when it's stretched 1.5 centimeters. And D, for what values of x does the speed equal 1/2 the maximum speed? So I've got a little diagram over here on the side. This right here marks the equilibrium position. Since we've compressed it 4 centimeters, we'll assume that it's going to oscillate 4 centimeters on each side of that. How do we figure out the maximum speed? Well, using the energy ideas, what do we know has to be true in this case? Well, all of the elastic potential energy we gain by compressing it 4 centimeters is going to be converted into kinetic energy. When does that happen? Well, of course, it happens at this equilibrium position right in the middle. So in this case, how much energy does it start out with? Well, 1/2 kA squared, where A is the amplitude, how far it's compressed to begin with, and that's all going to be converted into 1/2 mv squared. Plugging in our numbers, spring constant, the displacement, the mass of the object, and we can calculate the velocity, which in this case is 0.28 meters per second. Part B, the speed of the object when it's compressed this far. Again, we're going to use energy conservation, but in this case, all the energy it starts out with is going to be converted both into kinetic and potential. In this case, the energy it starts out with, 1/2 kA squared, where A is the amplitude, the 4 centimeters, is converted both into, and when it's compressed 1.5, it still has some velocity, and it also still has some elastic potential energy, 1/2 kx squared. Plugging in our numbers, the 1.5 centimeters becomes that, and if we solve it, we'll discover, doing some more math, the velocity is 0.26, almost as fast as its at maximum velocity, which happens at equilibrium, but not quite. C, what happens if it's compressed that far? Well, in this case, the only difference is the compression distance is now negative 0.1015. Because it's squared, we lose the negative sign, and it's probably pretty obvious it's going to be the exact same velocity. Finally, D, for what values of x does the speed equal 1/2 the maximum speed? Doing the same sort of thing with energy conservation. In this case, where the maximum speed we just determined was 0.28 meters per second. That was from answer A. So over here, we're just going to plug in half of that. That gives us the 0.14 meters per second here for the kinetic energy, 1/2 mv squared, plus 1/2 kx squared equals the total energy. And if you solve this just mathematically, you'll discover that when the x position is equal to 3.46 centimeters, or 0.0346 meters, this equation becomes true. I hope this helps. Lots of energy.